So, Assalamu alaikum, all of you. I am Abdullah Momin from KMES English Medium High School and Junior College. And in this video, we are going to see the second part of our numericals from the chapter Superposition of Waves. So, in our first part, we have seen numericals 6.1, 6.2, and 6.3. Now, in this video we are going to see numerical 6.4 and onwards. So first we are going to solve the numerical 6.4, which is on page number 145 of your textbook. So what is the numerical? So example 6.4, an air column is of length 17 meter long. Calculate the frequency of fifth overtone if the air column is A, closed at one end, and B, open at both ends, and the velocity of sound in air is given, which is 340 meter per second. So we are supposed to find out the frequency of fifth overtone. So in order to find out the frequency of fifth overtone for a pipe which is closed at one end and for a pipe which is open at both ends, so length of the air column is given, that is 17 centimeter. We will convert this length into meter and it can be written as 0.17 meter. Now we are supposed to find out the overtone, fifth frequency of fifth overtone. So we will write the overtone number is 5 and the velocity of sound in air is 340 meter per second. Now for an air column which is closed at one end, we have the formula of fundamental frequency n is equal to V by 4R, where V is the velocity of sound in air and L is the length of the air column. So we will put the value of V and L, and after calculating we will get 500 Hertz. That is the fundamental frequency, but we are supposed to calculate the frequency of fifth overtone. So in order to calculate the frequency of fifth overtone, for fifth overtone, NP is equal to 2P plus 1. That is when the pipe is closed at one end. So this is, instead of P we are going to put 5, and instead of N is the frequency, fundamental frequency. So we will write 500, and after calculating it we will get 5500. So this is the frequency of fifth overtone for a pipe closed at one end. Now we will solve, similarly we are going to solve the frequency of fifth overtone for a pipe which is open at both ends. So first we will calculate the fundamental frequency, and the formula of fundamental frequency for a pipe open at both ends is equal to V by 12. So instead of V, that is V is your velocity of sound in air, and L, that is your length of the pipe. So we will get N fundamental frequency as 1000 Hertz. Now for a pipe which is open at both ends, the fifth overtone or pth overtone, NP is equal to P plus 1N. So we will write, for fifth overtone we will put 5. Instead of P we will put 5 plus 1 into N is where 1000. So 5 plus 1 6 into 1000 means 6000. So this is 5500. That is the fifth overtone frequency for the pipe which is closed at one end, and for the pipe which is open at both the end the frequency is 6000 Hertz. Now next numerical, that is example 6.5, textbook page number 145. So the question is, a closed pipe and an open pipe have the same length. Though there are two types of pipe, one is closed pipe which is closed at one end, and another one is open pipe which is open at both the end. So we have to show that no mode of the closed pipe has the same wavelength as any mode of the open pipe. So for a closed pipe, that is a pipe closed at one end and open at other end, the frequency of allowed modes is given by, that is 2p plus 1 nc, that n that is the frequency of pth overtone, that is the fundamental frequency of closed pipe. So nc can be written as 4 by 4l, and nc is equal to 4 by 4l. So using this equation, where p is any integer, the wavelength can be written as 4l upon 2p plus 1, where p is at any integer. So that is the wavelength of the closed pipe, that is 4l upon 2p plus 1. Now, on the other hand, for an open pipe that is open at both ends, the frequency of allowed modes are 2l divided by m plus 1, where m is any integer. And if we will write frequency of closed pipe is equal to, it would mean that 4l divided by 2p plus 1 is equal to 2l divided by m plus 1. If the length is same, that means l and l get cancelled, and when you will cross multiply it, you will get 2m plus 1 and 2p plus 1, which is not possible from this equation. So if it is not possible, hence we will say that the two pipes cannot have modes with the same frequency or wavelength. So next is your example 6.6 from textbook page number 147. So what is the question? A string is fixed So if we are saying that the string is fixed at both ends, what is the ratio of the frequency of the first harmonic to that of the second harmonic? So if a string of length L fixed at the both ends, the wavelength of the first and second harmonic is given by L is equal to lambda by 2 and L is equal to lambda 1. And the ratio of their frequency will be n divided by n1 is equal to v by lambda divided by v by lambda 1. We will get cancelled. Denominator of this denominator becomes numerator. So we will write lambda 1 by lambda. And lambda 1 is your L and lambda is your 2L. So we will write L upon 2L. L and L get cancelled and it can be written as 1 by 2. So the ratio of the frequency of first harmonic to that of second harmonic is 1 by 2. Next is your example 6.7. So in this example, what is given? The velocity of a transverse wave on a string of length 0.5 meter is 225 meter per second. A. What is the fundamental frequency of a standing wave on this string if both ends are kept fixed? B. While this string is vibrating in the fundamental harmonic, what is the wavelength of sound produced in air if the velocity of sound in air is 330 meter per second? So we are supposed to find out the fundamental frequency if both ends are fixed, and if the string is vibrating in the fundamental harmonic, what is the wavelength of the sound which is produces, and the velocity of the sound is given. So the wavelength of the fundamental mode is lambda is equal to 12, and the fundamental frequency n is equal to v by 12, and instead of v we will put 225, and instead of l we will put 0.5, so we will get 225 per second, that is hertz. So the frequency is 225 hertz. While the string is vibrating in the fundamental harmonic, the frequency of the sound produced by the string will be same as the fundamental frequency of the string. So the wavelength of the sound produced is lambda is equal to v by n, and v is 330, n is 225, and when you will solve this you will get 1.467, that is the wavelength. Now numerical 6.8 or example 6.8 from the textbook page number 148. So a string 105 centimeter long is fixed at one end. The other end of the string is moved up and down with frequency 15 Hz. A stationary wave produced in the string consists of 3 loops. Calculate the speed of progressive wave which have produced the stationary waves in the string. So what is given here? So the length of the string is 105 centimeter in 3 loops. That means the length of the one loop is lambda by 2. So if it is 3 loop, so we will solve the wavelength lambda as 3 by 2 goes another side of this equal sign. It becomes 2 by 3, or we will write 2L by 3. So from this equation, we can write lambda is equal to 2 by 3L. And L is 105. So when you will solve this, you will get 70 centimeter. That means 0.7 meter. So the lambda is 0.7 centimeter. But we are not supposed to calculate the lambda. We are supposed to calculate the speed of the progressive. And we know that speed is equal to frequency into wavelength. So frequency is 15 hertz, wavelength is 0.7 meter. So we will get speed as 10.50 meter per second. So this is your numerical 6.8. So that's it, student. That is all from this video, and some more examples we will see in our next video. I will catch you next time.